This is the do file for the tobacco project. I called it smoke.dta. So that's online. That's data on Blackboard for the course website. This is what we do every week, at least every week that we use Stata. So we open the do file from Blackboard, and the do file opens on Stata once you have Stata installed. I'm just trying to make it so I can switch back and forth between the do, what they call the do editor here, where it has the code, and then the Stata, what they call the console here, where it puts all of the output. This is the data from chapter 11 of the book. I'm on page 272 of the book, where they have case study 11.1 on smoking, heart disease, and lung cancer. So I copied the data from the book here into your Stata file. So this is what the data looks like. You have non-smokers, and then you have people smoking at sort of different levels. You have the incidence, so like the amount of lung cancer, and then you have P years, which are person years. Person years are when you follow people over time. So if someone's in the study for only half of a year, that's called 1/2 of a person year. If someone's in the study for 75% of the year, that's 75% of a person year, or 0.75 person years. Because not everyone's in the study for the entire year, and that's how you take into account that people are dropping out of the study, or people are moving in and out of the studies, what they call attrition, people dropping out of studies. Right? You do a study and they don't complete the survey, or they move and now you don't have their address, or you call them and they don't answer their phone. And the IR command in Stata, now this does what's called the incident rate comparison. So this is what they're asking on page 273 of the book, what's the incidence rate for various levels. To simplify the problem, I'll just compare smokers to non-smokers regardless of how often they smoke. So the first thing it does is it puts that into the table at the top. So you see 250 deaths, 16,000 person years, and then you get 0.015, so that's 1.6% of the people had cancer from that exposed group for people who were smoking. Unexposed, so non-smokers, that's 0.0027, so that's less than 1%, right? That's 0.27% or 0.28% of people in that group. So how it does that is it just divides the incidence or the deaths divided by the person years, and that's what they call the incident rate, and it does that for smokers and non-smokers. You could see in the data I had non-smoker is 0, doesn't smoke at all, and then the different amounts of smoking, those are all 1, so just compare smokers to non-smokers. So what it does is it adds up all the deaths, adds up all the person years, puts them into smoker, non-smoker. Calculates the incidence rate, so incidence rate's the deaths divided by the number of person years. And then if you shift those over, multiply by 100, those are percent. So 1.56% for smokers, and then 0.27% for non-smokers. And then it compares it to see whether smoking is correlated with incidence, or smoking is correlated with deaths, or smoking is correlated with lung cancer. And the p-value is 0.0000. That's statistically significant, right? Remember, really low p-value, really small p-value, that means that the result is statistically significant. If it's not statistically significant, you can't say smoking is related to cancer, or you can't say it's related. You cannot say that it's correlated if it's not statistically significant. If it's a really high p-value, you need to say something like, we need to collect more data, or the study's not big enough, or we could not detect a difference. Really small p-value, you say, yes, we have enough data and we found a difference, and there seems to be some type of relationship between smoking, heart disease, and lung cancer, either smoking causing cancer, cancer causing smoking, or some third thing causing both of those. Now, if you make a new variable, G is generate, so you see I divided deaths by person years. So make a new variable called cancer, divide death per person years. That's how I get mean of cancer, which is the rate here. Again, they're percents. So that's a little between 3% and 4% of people who are smoking over half a pack a day had lung cancer. And this is called a dose response, a step function or a dose response, because it means that the higher the dose of smoking, the greater the risk of lung cancer. So greater rates of smoking, greater rates of lung cancer, from non-smokers 0 to less than a pack to 1 to 2 packs to over 2 packs. And it increases with each amount. So the more they're smoking, the higher the risk. That's called a dose response. So yes, there is a dose response, because it keeps increasing with each increasing level. So to review, so here's the data here. 250 divided by 16,000, 0.015, 1.5%. 50 divided by 10,000, 0.002, 0.2%. Two-sided p-value 0.0000 at the bottom. Two-sided p-value tiny, 0, less than 0.00001. Yes, statistically significant. And yes, a dose response. Really tiny p-value, statistically significant. Bars keep increasing with greater amounts of tobacco use. That's called the dose response. So in the book, they ask you to look at the incidence rate and then to look at the dose response. So we see that it's statistically significant, yes, statistically significant, yes, dose response. And this is what I'll ask you in the quiz for the week. And I'll use the same data for the quiz questions. So just to review it, and we'll go over this in the slides as well. So if you had a really big p-value, if the p-value was, say, 0.9, remember it has to be between 0 and 1, but if it was 0.9 or 0.8 or 0.7 or 0.6, well, that's not statistically significant. If it's 0.000001, or if it's basically stated, we'll call it 0, then it is statistically significant. So yes, statistically significant, because the p-value is very small, basically 0, and yes, dose response, because that graph keeps increasing.